And today I'm going to talk about some kind of new way to do quantum field theory and to understand the gapless state in the very systematic way. So we know that there are three kinds of quantum matter. The first kind is the one with an energy gap, which have a no low energy excitation. It's kind of trivial. A second kind is have a few low energy excitations, like a superfluid crystal, and also like a critical point. These we can say they are interesting and very interesting. And the third kind is like a Fermi liquid, where the Fermi surface, there's a lot of low-lying excitation. So it's very messy, very complicated. And so today I'm mainly trying to concentrate on this interesting one. So actually, the trivial one, basically including topological order, topological insulator, and etc. We now have after 30 years, we gain quite a systematic understanding of those trivial ones. And so I think now probably we should go to next stage to do the interesting one. Then hopefully we can do some messy one. And the way to approach this interesting quantum matter, or another way you can say the strongly correlated gapless state. And we think maybe the symmetry should play a very important role. In particular, there's a proposal that this emergent symmetry have a chance to fully characterize these gapless states. So it's like a topological invariance for topological order. So symmetry may be like we can call geometrical invariance for gapless states. If you know all the geometrical invariance, we fully characterize the gapless states, then we can develop a systematic theory. However, the emergent symmetry at low energy in gapless state can be very, very general. Okay, so they're usually beyond the group, and they can also have an anomaly. So it's a very, very general symmetry. So that is what is making it possible to use a symmetry to fully characterize a gapless system. And so it turns out that this trivial quantum matter and the interesting quantum matter have a close relation, because this generalized symmetry can be described by topological order in one higher dimension. So this topological order in one higher dimension can be viewed as a unified description of all emergent symmetry. So there's a very systematic theory for emergent symmetry or for generalized symmetry, not in terms of group or higher group, not in terms of anomaly, but in terms of topological order in one higher dimension, or in terms of some kind of a fusion higher category. Okay, so if you combine these two, and it's propose a new direction to do quantum field theory, we can call this called the algebraic quantum field theory. So this kind of algebraic way, or maybe number theoretical way, to understand the gapless quantum matter. Okay, so this is a kind of a picture I try to present today. So there's several concepts which involve. So let's explain some concepts quickly. So first, what is a topological order? So in some sense, a topological order is can be characterized is a gapped quantum phase, so which can be characterized by topological excitation. The topological excitation basically is an excitation that cannot be created alone. For example, we can have a topological order given by the string liquid. This string can be viewed as the downspin. Downspin may form a string in the background of upspin. And then this string liquid actually is an example of a topological order. And in this string liquid, we can have this open string excitation. But the middle part of open string is kind of merged with the background closed string liquid. So it's not observable. Only end of open string is observable and behave like a topological excitation, point like topological excitation. And from here, you can see that clearly we cannot create a single end of a string alone. We have to create them in pairs. So this is one of a simple way to understand the topological excitation in topological order. And those topologication can fuse, can braid. So formally, actually, they are described by this so-called braid fusion category or fusion hierarchy category. So that is the mathematical language to describe excitation in any condensed matter system, a quantum liquid system. But this fusion category and the hierarchy category or braid fusion category is kind of abstract. And such, actually, there's a more simple data to measure and define topological order. Maybe not fully, but almost. And the simplest data basically is a ground state degeneracy on the space with some non-trivial topology like a torus or genus 2 Riemann surface and etc. But degeneracy is not quite enough. Actually, there is even more extensive, more informative data. That is called a representation of a mapping class group. Basically, mapping class group is a group that map a space into itself. And so under this mapping class group action, the ground state may transform, and how the ground state transform may give rise to actual data. For example, this psi alpha psi data label ground state, and we can consider overlap two ground states, but differ by this 90-degree rotation. This is a 90-degree rotation. And because our system do not have 90-degree rotation symmetry, so overlap is very tiny. So that's exponentially small in terms of area. Okay, so this is two-dimensional system. But however, if you remove this exponential small non-universal part, actually there's a universal constant part do not depend on area of the system. And this is basically defined as S matrix. And we can also do another explanation, which is a Dane twist. We kind of shear twist the space like this. And then this Dane twist also gave rise to this wave function overlap. Again, very small, but removing this small part, we get a T matrix, which is unitary matrix. It turns out that this unitary matrix form this representation of SL2Z. Actually, this 90-degree rotation and this Dane twist generate this SL2Z group. Then naturally, this overlap from representation of this SL2Z group. So this ST matrix is very useful data and simple data to characterize a two-dimensional topological order. So this is something we can put a hand on. Yeah, it's very practical. Okay. So the next question is that why symmetry and the topological order in one higher dimension have any relation? These two seems very different things. Okay. And to see this connection, so let's consider this 1+1 dimensional transverse Ising model. Okay, which have a Z2 symmetry generated by this spin flip. Okay. So under spin flip, there is a so-called local symmetric operator, which is generated by this X and 2Z. So basically, this algebra of local symmetric operator is the most important thing, which actually determine all the physical properties of the system with the symmetry. So let's look at this local symmetric operator. And under the action of a local symmetric operator, that's all the possible time evolution we can do with this symmetry. Then we find that there is a conservation. There's a conservation law. Something conserved under action of all those local symmetric operators. So one conservation law, we can see that we can choose its left or right basis in this model. Okay. And then we can, so on the background of a right spin, we have a few left spin. Okay. Then you can check that under this action of this 2Z operator, then only the left spin can move around, but they cannot disappear. Okay. And under X operation, the left spin just don't do anything. So you can see that so there's a mode 2 conservation of a left spin. So this operation can create a pair of left spin, but it cannot create them alone. So that means that there's a mode 2 conservation of a left spin. Okay. And actually there's another conservation law. We can choose this up and down basis. And so and consider domain wall between the up and down. Again, under this operation, we can only create a pair of domain wall or moving domain wall around, but we cannot create a single domain wall. So again, there's a domain wall also have a Z2 conservation. And the first Z2 conservation we call the Z2 symmetry, and the second Z2 conservation we call the Z2 dual symmetry. So we want to combine these two symmetries together. The combination of the two symmetry is called the categorical symmetry. So in some sense, the categorical symmetry is a kind of putting this order parameter and disorder parameter together. So put these two things together. So this is a notion of a categorical symmetry. So how to understand this combined symmetry or this categorical symmetry in more detail? And here we will consider a pair creation operator of the symmetry charge. You can see a pair creation operator of symmetry charge actually is a string operator. Now we can multiply this ZZ operator on the neighboring side together, and to obtain a ZIZJ operator, IJ can be far away. And this sort of operator create two left spin, so they're creating pair for Z2 charge. Okay. And the pair for dual Z2 charge can be created by another string operator, which is a product of X, which is like doing a similar transformation, but only in the patch, only in the local region. So and this operator create two domain walls. So those are two operators which create a pair of symmetry charge. Okay. Then from these two operators, we realize that actually these two symmetry do not combine to this simple Dirac product of two symmetry, really because these two operators have non-trivial algebraic relation, and we call them pi mutual statistics. Because when these two operators straddled in this way, so like IJ and KL kind of straddled in such a fashion, then these two operators kind of undercommute. You know, if they are two independent symmetry, the charge pair creation operator will be always commute. And here they undercommute. But however, if not straddled, they commute. So it depends on whether these two how the relation between this positional relation between two operators. And this is kind of because this commutation relation is kind of like if you view this order of operator as time direction, and then this commutation relation almost like braiding one particle. We view end of a string as a particle, braid one Z2 charge around another Z2 charge, and there's a pi phase. So that's this operator algebra reveals something non-trivial, which looks like mutual statistics, which is defined only in one higher dimension. Okay. And so because it's non-trivial relation, so that's why we denote this combined symmetry using V, not using Dirac product, some non-trivial combination. Okay. So in general, so this is just an example, and but this example demonstrates two general features. One feature is that the algebra of this local symmetric operator actually contains extended operator like this string operator. They are actually product of this local symmetric operators. Okay, and then the algebra of extended operator can be non-trivial. Actually, the algebra of extended operator actually encode a braid diffusion category. So this is a basically we try to say that the algebra of a local symmetric operator encode the braid diffusion category, and this may be one way to see the symmetry and the topological order may be related. Okay, so really multiply this picture actually again using this example, we can really see that this Z2 symmetry or this categorical symmetry are related to the topological order in one higher dimension, that's in 2 + 1 dimension. This topology is very simple, it's just a Z2 gauge theory. The Z2 gauge theory is like a Turing code, have 4 extensions. It's a 1, E, M, and the combination, the F fermion. Okay. And in this case, obviously we see that this E have a mode 2 conservation because this fusion rule. And also M also have a mode 2 conservation. So therefore in the bulk, the conservation of an E particle, mode conservation of E particle like this Z2 symmetry we discussed in one dimension, and the mode conservation of M particle like a Z2 dual symmetry in one dimension. And also in the bulk, this E and M have a pi mutual statistics. So you can see that this topological order in the bulk model this operator algebra in one lower dimension quite nicely. Okay, and so to actually we can understand better why the 2 + 1 dimensional bulk is related to the 1 + 1 dimensional boundary. Okay, and to see this connection between bulk and the boundary more directly, and we notice that in the 2 + 1 dimensional bulk, we have this E particle, Z2 charge. This can condense. If they condense, that's basically the Higgs phase. And this Higgs phase would give us this a trivial topological order. Okay. So basically the E condensation would give us a trivial topological order. And then we can imagine that there's a domain wall between this trivial topological order induced by E condensation and the Z2 gauge theory. And then this domain wall is also gapped. Okay. And then we say this domain wall is induced by the E condensation. So I'm using this picture to introduce notion that the boundary of this topological order to the vacuum, to the trivial state can be viewed as condensation of some particle in a topological order. Okay. In this case, in this example, it's an E condensation, is like Higgs condensation. Similarly, we can have M particle can also condense. The condensed phase is called the confined phase. And this confined phase also have a trivial topological order. So therefore, M particle condensation can also induce a gapped boundary of Z2 gauge theory. Okay. So that's the boundary and the condensation are related. So that's the point I try to make here. And so let's consider a boundary which induced by M condensation. And certainly 1 always condense. So actually this boundary is induced by the 1 and M. And so this combination condense. Okay. And what happened to the boundary? Because M condensed, but so M particle to the boundary just condense disappeared. So in a sense, it's like this because M is a dual Z2 charge. So this dual Z2 symmetry is spontaneously broken by M condensation. But the E particle go to boundary still remain to be a well-defined particle. So therefore, the Z2 symmetry is unbroken. So actually, the 1 condensed boundary corresponds to this Z2 symmetric phase. And but this break this this dual Z2 symmetry. And similarly, this E condensed phase spontaneous break this Z2 symmetry, but the Z2 tilt is not broken. So that corresponds to Z2 symmetry breaking state in the Ising model. Okay. And one thing I want to emphasize here is that in the Ising model, the Hilbert space contains both this even charge and odd charge excitation, a Z2 charge. But however, on the boundary of topological order, we only have even E particles. We don't have even Z2 charge. So therefore, this boundary of a topological order do not quite exactly match the transverse Ising model. But however, because they only have even Z2 charge, they actually match this so-called Z2 symmetric sub-Hilbert space of Ising model. So and this is very important. So boundary of a topological order indeed describe a symmetric system in one lower dimension, but really they only describe the symmetric subspace of the symmetric system in one lower dimension. And a similar thing is true for this for E condensation. Again, the boundary only contains even number of M particles, so therefore only describe the symmetric subspace which contain this this dual Z2 symmetry symmetric subspace. Okay. And then we can also have this the other possibility. That is we do not condense, nothing condense. Okay. If nothing condense, then this boundary actually have a full categorical symmetry. Okay. And this full, the boundary with a full categorical symmetry actually is a gapless state correspond to the transition, phase transition boundary between this Z2 symmetry breaking state and Z2 symmetric state. Because in the Z2 symmetry breaking state, we have the dual Z2 symmetry. In the Z2 symmetric, in the dual Z2 symmetry breaking state, we have a Z2 symmetry. Then at their boundary, they have both dual Z2 symmetry and a Z2 symmetry at their boundary. So therefore, naturally, the boundary preserve all the symmetry. And amazingly, this boundary must be gapless. So the system with the full categorical symmetry must be gapless. Okay. So this is something very special about this about the categorical symmetry, because these two symmetry, Z2 symmetry and dual symmetry, can have a mutual statistics. So as one consequence that we cannot break both symmetry, because this E and M have mutual statistics. We cannot condense both of them. Okay, so we cannot break both symmetry, but we can break one of them. If we break one of them, we can get a gapless state. But however, if we do not break any of them, then the resulting state must be gapless. And there's for Z2 symmetry, there's a kind of rigorous proof by Michael Levin. And we also have some more general argument using modular transformation to show this. So this is supposed to be generally true. Okay, so this gave us some kind of general picture example how the categorical symmetry was used, how they are related to the gapless state and the low energy dynamics. So any questions? Any question? Feel free to interrupt me. Okay. So we just discuss Ising model about this notion of categorical symmetry. And actually, for any symmetry, we have this corresponding categorical symmetry. And so there's the issue how to compute categorical symmetry. And there's also a holographic computation. So the idea is, for example, we can have this n-dimensional anomaly-free symmetry. And this symmetry can be higher symmetry if this G is a higher group. Okay. Then we know that for the anomaly-free symmetry, this symmetry can be realized by the product states, by the product state with symmetry. Okay, and this product states with symmetry can be viewed as a boundary for one higher dimensional trivial product state, because the product state doesn't matter which dimension. We can always add a product state to go to higher dimension. Okay, and because it's a product state with symmetry, so we can gauge the bulk symmetry, and then that when you gauge bulk symmetry, then we get a topological order in one higher dimension described by this G gauge theory. And so gauging the bulk symmetry is a way to produce a categorical symmetry. And this works even for anomalous symmetry. Because if you have anomalous symmetry, then the system can be viewed as a boundary of one higher dimensional SPD states. Okay. And then we can gauge the bulk symmetry in the SPD states. What we get is a Dirac-Witten model. So therefore, for anomalous symmetry, also have a categorical symmetry, which is a Dirac-Witten model, or higher, or Dirac-Witten model for higher gauge theory. That if you have a higher symmetry. Then from here we see that we cannot but topological order in one higher dimension is can be go beyond the Dirac-Witten model. Okay, there's a more topological order than Dirac-Witten model. So this really raises an interesting possibility, is that maybe we have some kind of symmetry, a generalized symmetry, which are beyond anomaly-free symmetry, also beyond anomalous symmetry, regardless of higher or not higher. Okay, so this is a more general topological order describing some more general symmetry, and that we call the algebraic higher symmetry. and which actually now commonly not known as this non-invertible symmetry or non-invertible higher symmetry, or maybe anomalous non-invertible higher symmetry. Basically, kind of including those kind of things. So topological in one higher dimension can describe all those generalized symmetry. Okay, so here now let's try to describe give some general description of this algebraic higher symmetry. But here we try to concentrate on this anomaly-free algebraic higher symmetry. So basically, we want to study the non-invertible higher symmetry. What is the general theory for this non-invertible higher symmetry? And one way to describe symmetry is to consider excitation. First, this anomaly-free means that for higher symmetry or for general symmetry, anomaly-free means that it allows a gapped non-degenerate ground state on space on the sphere, you know. And so this condition basically try to remove this spontaneous possibility of spontaneous breaking. When you have spontaneous breaking, the degeneracy will be not 1. Also, for anomaly-free, for anomalous symmetry, and we may have either we break symmetry, which have a degeneracy, or they have a gapless excitation. So again, this condition also remove the possibility of anomalous symmetry. So this one simple condition is enough to specify anomaly-free condition. Okay. And then another point is that this anomaly-free symmetry can be fully characterized by their excitations. And those excitations are called a symmetry charge, basically. And above this non-degenerate ground state. And those excitations can fuse and break. So in a sense, this anomaly-free symmetry can be described by this fusion n category if our space is n-dimensional. Yeah. So this is kind of general message. Using the fusion and the breaking of symmetry charge, we can fully characterize a symmetry. But because symmetry charge can be point-like, can be string-like, can be membrane-like, so actually in higher dimension, we need to consider a higher category to fully describe a symmetry. And this description can go beyond a group, and higher group can include non-invertible symmetry. Okay. And just similar to the Z2 symmetry, this anomaly-free symmetry R, so this now I view R as this fusion n category, also have a dual symmetry we call R tilde, which is also a fusion n category. Okay. So then the combination of a symmetry and dual symmetry would give us a categorical symmetry. So they're kind of similar. But certainly this combination is kind of very vague combination. So exactly how to define the combination is tricky. But actually, this combination of the two symmetry can be defined more rigorously mathematically as so-called as a center for this R or center of R tilde. Actually, the two center is the same. Okay. For symmetry and dual symmetry, they have the same center. And this center is a braid fusion n category. Actually, they describe a excitation in topological order in one higher dimension. So this is this really led to this holographic picture. Okay. So I just mentioned that the symmetry charge form this fusion n category R. And the topological order in one higher dimension also have excitation. And those excitations form a braid fusion n category, which is called M. And the symmetry charge and the R and M have the relation by this center. And this relation have this physical meaning. Is that actually this symmetry charge appear as a boundary excitation of this topological order M. Okay. So because center have interpretation of a boundary bulk relation, so therefore the symmetry charge described by R can be viewed as a boundary of a boundary excitation of topological order M. Again, here we have similar constraint, and the boundary for this topological order M actually corresponds to the R symmetric subhyperspace, you know. they only contain something like an even symmetry charge, or they only contain the total neutral sector of the symmetry charge. But the individual charge, anti-charge can appear. Okay. And so actually, in my description above, there's an important qualifier I did emphasize, that actually the symmetry charge not only form a fusion N category, actually form a special kind of a local fusion N category, which is called the local fusion N category. So therefore, we cannot say that a fusion N category describes symmetry charge and describe a symmetry. No, only the local fusion N category describe a symmetry. So therefore, it is only local fusion N category replace a group and a higher group. It's a mathematical foundation for anomaly-free symmetry. But what the local means, then using this holographic picture, we can explain local very easily. So remember that for the symmetry, we have this associated categorical symmetry, which is a bulk. Okay. Then if R is a fusion category describing boundary excitation. Okay. And if we have another, if this M have another boundary, whose excitation are described by R tilde. So R tilde means another boundary. Okay. And then we can have this sandwich structure, which is the M have two boundaries, R and R tilde. And we can stacking these two boundaries together via this M. So this has this notation. No, I think I make a mistake here. And so let me take it. So I'm not so yeah, I do not have this. There's no center here, so this is a mistake. Okay. So the stacking between So the stacking between these two boundary R tilde via this center, via this bulk is related by this. It's a box product with R tilde via this bulk M. So it's this notation. If this stacking give us some, we can view this slab as a system in one lower dimension. So in n dimension. If this slab describing a trivial topological order, you know, and then we say this both R are local. So local really means that we require R and R have another fusion category. They're stacking through M, become trivial. The physical motivation is the following. You can see we can just add an arbitrary layer of topological order to one boundary. And to have a lot of topological excitation to the boundary by adding some layer of topological order to the boundary. And this actual topological order has nothing to do with symmetry. And so when you add this actual topological order to the boundary, then we cannot find any R tilde which cancel this topological order, because topological order is a kind of monoid. We cannot cancel it. Okay. And so therefore, this condition just remove this possibility of stacking actual topological order to the boundary. And so it's like something like this R boundary is somewhat minimal. You know, it's kind of small boundary, have no actual excitation except those come from the symmetry. So therefore, this condition define the notion of a local fusion N category, and the local fusion N category replacing the concept of group and higher group, and it's a kind of unified way to describe so-called anomaly-free symmetry. Okay, and this picture, holographic picture, also have a very physical meaning. So let's try to describe same picture, but using a little bit more physical interpretation. So remember this anomaly-free symmetry. Anomaly-free symmetry would allow a trivial symmetrical ground state. this trivial symmetric ground state actually is a product state. Okay. So basically, is that we have a product state which have a symmetry. So that's the point. This product state is described by this in category language described the trivial category is NVec. So the NVec corresponds to this product state. Okay. So then we are facing a task. Given a product state, how do we know this product state have a symmetry or not have a symmetry? Okay. So then we say that if this product state, this product ground state, plus its extension above it, allow this decomposition. So this product state can be viewed as this kind of decomposition. Then this decomposition exposes the symmetry hidden in the product state. So that's another picture. And so basically that's if the product states and the extension above this product ground state can be reproduced by this sandwich structure, by this decomposition, and then we say that this product state actually have a symmetry. So there's a way to detect symmetry is to say whether the product state have a decomposition or not. And this decomposition really say that have an assumption that this M and the R tilde boundary have an infinite energy gap. So only the boundary extension of this R boundary match the extension above this product states. Okay. So therefore, this picture actually is a picture of emergence of symmetry. We have a product states, and we don't know whether there's symmetry or not. Then we try to see whether their extension can be reproduced by this composite system. If yes, then actually this product state would have an anomaly-free symmetry. This R actually, yeah. Okay. So this is this is really the central thing. So this decomposition reveal the symmetry. Again, this decomposition is written as a R tilde tensor product through this M. So this is a very formal mathematical notion of a tensor product. Actually, have a very geometrical physical interpretation as this stacking structure, stacking through a bulk basically. And that picture actually is very important because that picture can be generalized to any state. Because here we consider a product state. We try to test whether product state have a symmetry or not. We can start with any state, like a topological or gapless states. You know, topological order or gapless in any state, C bar, C under bar. Okay. And then we want to ask whether this system, the ground state plus extension above it. So that's what we mean by a system. The ground state plus extension above it, whether such a system can be have a symmetry or not. Again, similarly, if you say this system allow this decomposition, means it have a combined system like this, which kind of reproduce a low-lying extension of this original system. Then we say that this system have a symmetry. This symmetry is M is called categorical symmetry, and R is called this symmetry. Yeah. So maybe this is a central message here. So the central message is this kind of holographic way to see symmetry or no symmetry. The most important thing is that this combination composite system reproduce low energy extensions. So therefore, this original system and the composite system have same partition function. So that is the meaning of this decomposition. When you write this decomposition, it means they have same low energy extension. Their partition function at the low temperature is the same. Okay. So now you may see that the picture we described here is similar to this ADF CFT picture. So indeed, in the ADS-C picture, there's a statement, there's an original I quote from the Witten, that if the ADS theory have a gauge group, that implies that the boundary CFT would have a symmetry. This reference 13 is a Martinez paper. Okay, and so that's really just what described that the boundary symmetry kind of map to the bulk gauge group. But however, the picture we describe here, an ADS-C has some difference. In the ADS-C picture, they mainly for the continuous group. The symmetry always continuous, and they are group-like. Maybe we can say higher group-like. Okay. And but the example we described happen to be opposite. Our symmetry is finite. Actually, for continuous symmetry, we have a difficulty to have this holographic. Okay, because the bulk won't have a gap, and it can go beyond the group. Certainly include the group, but it can go beyond the group. So that's a kind of generalization to the ADS-CFT picture. And also, the ADS-C picture for continuous group, somehow there's ADS geometry, which is a very nice feature. But for us, we don't have a gap excitation, so we don't have a geometry. Basically, our results are independent metric, you know. Certainly you can add ADS metric, that's fine, but our results do not depend on any metric, so it's kind of topological. Yeah. So on one hand, the picture is very, very similar. On the other hand, there's some sharp distinction, sharp difference. Okay. So now let's try to continue and want to using this holographic picture to study CFT. In the ADS CFT picture, the main application is using this holographic picture to study CFT. And so here I want to do the same thing. But however, because our setup is quite different from ADS CFT, we don't have ADS. So therefore, our setup to study CFT is also different. But philosophically, there are some similarity that we can use a bulk data to determine the boundary CFT. And so this is using this generalized picture for the symmetry and to see how they have an impact on the boundary CFT on the gapless state. Okay, so how to use this non-ADS picture to do this to study CFT? Okay, so here we want to concentrate on the partition function. We want to concentrate on the partition function. We know that usually for the anomaly-free CFT, basically if a CFT can be realized by a lattice model, they call the anomaly-free CFT. The partition function of anomaly-free CFT have this modular invariance. So under the mapping class group transformation, they are invariant. So there's a modular invariance. So this modular invariance is closely related to this anomaly-free condition. Or maybe I think they are equivalent. Okay. Okay. However, in this decomposition, we say that actually our system, this modular invariant of anomaly-free CFT, have this decomposition can be represented in terms of this stacking of this topological order with two boundaries, have this composite system. And what do we mean by that? We mean that there is some topological order as a bulk. Then there's a gapless boundary. With the gapless boundary is anomalous CFT. Okay. And there's another gapped boundary we call the R tube, which is also is an anomalous gap state. So two anomalous gap states stacked with the anomalous gapless state through this bulk to produce our modular invariant partition function and produce our anomaly-free CFT. And here, to see this direct connection, we notice that anomalous theory, when the bulk topological order is non-trivial, this anomaly actually corresponds to non-invertible anomaly. Because this bulk topological order usually do not have an inversion which can cancel it. And so this anomaly, usually non-invertible anomaly, we can call this a non-invertible gravitational anomaly. So those anomalous CFT means it have a non-invertible gravitational anomaly. And the system with non-invertible gravitational anomaly are described by this multi-component partition function. So this is the key. They are described by multi-component partition function. And then, so similarly, the gapped boundary are also described by multi-component partition function. The difference is that if a boundary is gapped, the partition function do not depend on tau, because tau describing shape of space-time. So if system gap is topological, have no metric dependence, no shape dependence. So therefore, for gapped boundary, the partition function is constant. For gapless boundary, the partition function may depend on shape, have a tau dependence. Then we say that actually, the partition function of this combined system should reproduce partition function of an individual anomaly-free system. And the total partition function for the combined system actually is obtained by this inner product of these two vectors like a partition function. So it's just inner product, sum over this component, just a times each component and sum over. So like inner product of these two vectors like a partition function, and that produce a modular invariant partition function. So this will give a connection, how this modular invariant partition function can be obtained from this multi-component partition function, which are determined by the bulk topology order. Okay, and this is kind of abstract, and to really to see why we have a multi-component partition function, and we can rely on this picture, because the boundary partition function of topology order can be viewed as a partition function of this whole system. And so the bulk, this blue one is the topology order in the bulk, and the boundary may be gapless or maybe gap. Okay. Then because bulk have a topology order, we can imagine we can insert anion in the bulk. This word line of anion in the bulk. And this anion basically changing the boundary condition. But this anion far away from the boundary, so in some sense the boundary is not really changed, but get some twist. Okay. So therefore, different component of a boundary partition function coming from this different insertion for bulk anion, or coming from different boundary sectors. The boundary have different sector correspond to bulk insertion bulk anion, and so therefore this corresponds to the that give rise to the different component boundary partition function. Okay, so and so from this picture we can also see that this actually the boundary partition function is not modularly invariant but the modular covariant. And this is because we can rotate we can do the weak rotation. We can exchange this time and this radial direction. We can view the radial direction y as time, but the t as a y. Then this surface like a space, like a torus. The torus have this degenerate ground state. So in some sense, this multi-component partition function and the degenerate ground state wave function and the torus are kind of directly connected. And we know that the degenerate ground state and the torus and the modular transformation are kind of transformed like by this ST matrix. So from here we can understand or at least believe that this multi-component partition function also transform in the same way in terms of ST matrix characterizing bulk topology order. So this is another key result. That is the multi-component boundary partition function are determined by this ST matrix of a bulk topology order. Okay, so let's see. Let's just give an example using this Z2 example we discussed before. The Z2 gauge theory have 4 bulk anions. So the ST matrix are 4x4 matrix. So there are 4x4 ST matrix. Actually, T matrix describe self statistics. This -1 means this particle is a fermion. The +1 means these 3 particles are bosons. And this S matrix for the abelian topology are describing mutual statistics. So all those -1 here means there's a non-trivial mutual statistics between E and M. So So this entry is the EM is between E and M. It's 2 and 3. So 2 and 3 is E and M. Okay. And so that means have pi mutual statistics and etc. Okay. So this is the bulk topological order I described this kind of ST matrix. Okay. And then the one of a gapped boundary is that to obtain gapped boundary is the following. We just want to find a constant. So maybe I don't need to have this tau dependence. You can ignore the tau dependence. Okay. For the gap boundary, we don't have a tau dependence. Okay. So basically, that means we just need to find this we just need to find this this vector, constant vector, satisfying this modular covariant condition. Okay, and so then we find there are two solutions. Actually, using this estimation, we find only two solutions, and these two solutions correspond to this E condensed, M condensed, and really because you can see the for this boundary, this M component is 1. So that means that if I insert M particle, then we have a non-trivial boundary partition function. Okay, just like we have non-trivial boundary partition function 1 for the if you do not insert anything. However, if you insert E particle, then the partition function becomes 0. That means if I insert the E particle, and because this boundary is M condensed, so therefore we have a boundary non-trivial boundary excitation E particle. So they are not a ground state, and okay. So this E particle is the E particle is not ground state, have energies, and when you consider the partition function in the very low temperature, the partition function are exponentially small because of finite energy, and so that's why exponential becomes 0 in the thermodynamic limit. Okay, so this is this 1 in the M component means M condensed, and then the 1 in the E component means E condensed. So this really corresponds to these two boundaries. Yeah. Okay. And then clearly there's that's only for the constant partition function, that's only solution. And then we do not have a solution of this form. You know, if nothing condensed, we should have this kind of solution. Nothing condensed. This solution means nothing condensed. And this partition function can never be a solution of this can never be modular covariant. So therefore, that means if you do not break any symmetry, it must be gapless, because the constant partition function cannot be modular covariant. This kind of partition function cannot be modular covariant. So this is general proof why the partition function which do not break if you do not break categorical symmetry, the boundary must be gapless. Okay. So it's yeah. So so this is so therefore to obtain a partition function which do not have any condensation, we have to add tau dependence. So actually, when we have a tau dependence, indeed we have this modular covariant partition function. So this tau dependence partition function is constructed using so-called conformal character. This conformal character of a 4-3 middle model, or the conformal character of Ising CFT. Okay, using Ising CFT, somehow, because we know for the conformal character, we know how do they transform under certain under modular transformation. Then we just combine those conformal characters together so that they transform nicely under this particular ST matrix. Okay, so actually, another way to say that this particular asymmetry corresponds to a particular representation of this modular group. However, the conformal character usually form a different representation of modular group. But we can combine two representations to make up the particular representation we want. And that's how we obtain these results. And why these results have only this one condensation, do not have E condensation, M condensation. The reason is because this conformal character have this this called the conformal block. There's one conformal character or combination of conformal character. It's associated with a trivial primary field, means identity operator. So this component is a chi0 square. It's conformal character associated with a trivial primary field. And when we find this trivial primary field only appear in one component of partition function. So that means we only have one condensation. If this trivial primary field appear in other component, then that means we have some non-trivial condensation, and that break categorical symmetry. So here, this trivial component primary field only appear in the trivial primary field only appear in one component. That means we have a full categorical symmetry. So this particular partition function really described the gapless boundary with this anomalous gapless boundary with a full categorical symmetry, nothing breaking. Okay, so now we can combine those results. So we can do this. We can choose this anomalous CFT. So this Ising CFT is anomalous CFT describing by this multi-component partition function. And then this partition function can be have inner product, say with this one. So only first and the third component contribute. So means only this component and that component contribute. And then that gave us this modular invariant partition function. Okay. And we can choose another boundary one. So we can choose that boundary, this boundary as a gap boundary. Okay. And then do the inner product. So that's only first and second component. So that is only first and second component. Usually this different inner product would give rise to different modular invariant partition function. But for the Ising model, it's kind of special because this second and third component have the same thing. So they actually give rise to the same modular invariant partition function. But this is only special case for the Ising model. And so from here we can see that this modular invariant partition function of Ising model allow this decomposition and also allow that decomposition. So there are two different kinds of decomposition. And so it means that this modular invariant partition function of Ising model would have this Z2 gate theory in one higher dimension as categorical symmetry. But also that's emergence of categorical symmetry. But the emergent symmetry is a dual of the other boundary. And one is a E condensed, one is a M condensed. In mathematically is a rep Z2 and a vec Z2. So actually, the emergent symmetry will be the emergent Z2 symmetry or dual symmetry. There's two situations. Okay. So actually, these two pictures of assigning different boundary, assigning different gap boundary, actually represent this Kramer-Wiener duality in the Ising model. And so Ising model is self-dual under this duality transformation. So that's why the two models have same modular invariant partition function. But actually this picture also is a very general picture to construct duality. Basically by choosing different gap boundary, these two composite structure are related because they have same gapless sector, same local property, but globally they are different. So these are two globally different systems with the same local gapless structure. Actually, they are locally dual, so they relate to some duality transformation. So therefore, the duality, one way to construct duality is basically just choose all different gap boundary, then you can obtain all kind of duality of of any model you want. So this is really a systematic way to obtain all the duality model. Yeah, so that's a message in this slide already described it. Okay, and so there's okay. So there's a question here. So now in the last example we see that we can compute this anomalous CFT from the bulk topology order by constructing this modular covariant partition function. Okay, and so actually we are kind of hinting that maybe we can determine this anomalous CFT, or even determine this anomaly-free CFT from the emergent symmetry, maybe from the bulk topology order and from this gap boundary. So from this data, we probably can determine the CFT completely. Okay, and but actually this is not quite correct. Really, because if a given bulk topology order, we can have many different gapless boundaries. And for example, we can just stacking another anomaly-free CFT to this boundary and to obtain another boundary of the same topology order. So therefore, it seems it's far from true that the topology order can determine the boundary CFT. You know, there's too much redundancy, too much ambiguity, too much freedom here. Okay, but however, there's idea that when you're stacking another CFT to the boundary, this actual CFT may have its own emergent symmetry. So therefore, when you're stacking CFT, actually the combined the boundary may have a larger emergent symmetry. Okay, so therefore, that gives us some hope that if we explore all the emergent symmetry, then maybe you have one-to-one correspondence. Okay, so this one can be stated in a two way. Is that if we have if we consider the maximum emergent symmetry or maximum categorical symmetry, maybe this maximum symmetry can determine the CFT gapless system completely. Or if we have a given symmetry, then we have many CFT with that symmetry. But then maybe there's a single minimal CFT. Okay, and so therefore for the given categorical symmetry, maybe we can determine a minimal CFT. Or given CFT, maybe it can be determined from its maximum categorical symmetry. Okay, so this gives us some motivation trying to define what is the maximum categorical symmetry. You know, how do you say this CFT have emergent symmetry? How to determine this maximum emergent symmetry? Okay, so this really this picture, you can see that if you have a CFT, anomaly-free CFT, if the low energy excitation can be simulated by this composite structure, and here we require this boundary is only one condensed boundary. The gapless boundary is only one condensed. Okay, plus some another gap boundary. Then we say that this CFT would have emergent categorical symmetry M. Okay, and then we say that usually for a given CFT, anomaly-free CFT, it may admit many different decomposition like that. Then we just pick a decomposition where the M is a maximum. You know, the topology order is a maximum, and that is a maximum categorical symmetry, and that's it. So therefore, this decomposition picture, this holographic picture of the CFT, is very helpful to define this maximum categorical symmetry. And how to define maximum topology order, I don't know actually. But one way to define is motivated from total quantity dimension. So imagine usually the topological order have so-called elementary excitation. Okay, there's a notion of elementary excitation, which I won't explain here. And the elementary excitation is basically the topological excitation physicists talk about. Okay, but we do not include this descendant excitation induced by some other elementary excitation. Okay, those elementary excitation have a quantum dimension, basically representing internal degree freedom of this elementary excitation. And this quantum dimension not only defined for the point-like particle, also defined for the loops and for the sphere, for the membrane excitation. Okay. And then we can define this total quantum dimension as a sum of the square of an individual quantum dimension. And we can use total quantum dimension to define size of a topological order. So the topological order with a larger total quantum dimension, we call larger. I'm not sure this definition is suitable, but at the moment we can use this definition. Maybe okay, but maybe even there could be more suitable one. At the moment I'm not so sure. But anyway, this is our way to define this maximum categorical symmetry. And so then for the Ising model we studied. So what is a maximum categorical symmetry? It turns out that for this Ising modular invariant partition function, it has another decomposition. It can be decomposed into the double Ising topological order in a bulk. And the double Ising topological order have only one gapped boundary. We call this F boundary. Okay. And this composition actually can reproduce this modular invariant partition function. Okay. So that means that the maximum categorical symmetry of this modular invariant partition function actually is not a Z2 gate theory in the bulk. It's a double Ising topological order in the bulk. Okay, so that's one message. Okay, so we say that so actually this the Ising critical point have a maximum categorical symmetry given by double Ising model. Then one may ask a question: what is the emergent symmetry? Because double Ising model is the emergent categorical symmetry. The emergent symmetry will be given by this gapped boundary, or more precisely, the dual of the gapped boundary. Okay, so therefore, this gap boundary gave rise to the emergent symmetry for this. But here we have a problem. This gap boundary for the double Ising model is a fusion category contain these three excitations. And this fusion category is not local. So therefore, at least this gap boundary do not correspond to any anomaly-free symmetry. So therefore, so for the maximum categorical symmetry of Ising model, Ising critical point, there's no anomaly-free emergent symmetry. There's no corresponding anomaly-free emergent symmetry. And then we say maybe it have an anomalous emergent symmetry. That I don't know. And so actually, so actually in the paper by Fried and Talman, they try to define symmetry as this pair, any pair of this as a symmetry, and so that certainly that's an acceptable definition. In our paper, we try to say that when this gap boundary is anomaly free, it's a local fusion category, then you have an anomaly free emergent symmetry. Otherwise, we do not have anomaly free emergent symmetry. Okay. So anyway, so this is a way to introduce this maximum categorical symmetry for the Ising model, for the Ising critical point. Okay. So actually, the result we get here is actually it's general. It appears that the emergent maximum categorical symmetry for 1+1 dimensional CFT seems always have this doubled structure. It's a modular tensor category times another modular tensor category. Another one is a time reversal inverse or reflection inverse. And so in this paper, the Moore and Seiberg talk about some naturalness of the rational CFT. And this kind of holomorphic one, or this this diagonal combination of holomorphic one seems to play some natural role here. Okay. So now we give some another message here is that this diagonal one looks like have a maximum categorical symmetry, have this special meaning of a maximum categorical symmetry. Okay, so therefore we are hoping maybe this maximum categorical symmetry we have this one-to-one correspondence with anomaly free CFT. Okay, and at least one Platon dimension, because the categorical symmetry is have this double structure, we can consider one half it. So maybe for this for the chiral categories, we call this a half of this like chiral categorical symmetry. This chiral categorical symmetry maybe have a one-to-one correspondence with chiral anomalous, purely chiral anomalous CFT. Yeah, and so this is so this may be the message from here, from this doubled version. And then with this in mind, we can do this number theoretical calculation for this program. Actually, we do not know how to do this calculation, but this just expresses a wishful thinking. But I think it's a very important wishful thinking. And so this chiral anomalous CFT means that their partition function only depend on tau, do not depend on tau bar. So it's a holomorphic in tau. Okay, and it has this modular covariant condition, but in terms of this ST matrix of this chiral categorical symmetry, that's chiral part of a topological order. So you can also call this a chiral modular bootstrap. Everything is purely chiral. Okay, and this partition function for chiral partition function must satisfy this modular covariant condition. That's one of condition. And if you only use this condition, it's far from determining this function. You know, it's just some algebraic equation. And this is function. We can now determine a function using algebraic equation. Okay, we don't have enough equation. The function have infinite unknown, and we don't have finite number of equations. So there's a problem. Okay, and however, this partition function also satisfies another number theoretical condition. It's a number theory condition. That is, this partition function can be written as a polynomial of Q. Okay, Q is e to the 2 pi I tau, and there is some kind of Q with some fractional power. After we factor out this fractional power, then we only get a polynomial of Q with integer power only. But this polynomial is so special. This is a polynomial with only integer coefficient. The coefficient polynomial has to be integer, and also has to be non-negative integer. Okay, so I feel that these two conditions combined is very powerful. Probably can be determined this chiral partition function completely. Okay, and to say this is very powerful because this is a very popular conformal bootstrap, kind of using this kind of similar approach. But the conformal bootstrap do not use integer condition. They only use condition that coefficient is non-negative. And only use this non-negative condition already produce a very active field of study. Now I cannot imagine if you add this much stronger integer condition, what do we get? You know. But once you do that, this becomes number theory a problem. So probably we have to learn number theory. Okay. And then do we think this kind of chiral modular bootstrap determine the partition function completely? The actual answer is no, because there's a chiral partition function called the modular form. It's actually the partition function of an E8 CFT, which is invisible by this approach. Okay, so at least we have ambiguity of an E8 CFT. Okay, but the E8 CFT is a known ambiguity we feel we can handle. Okay, So this is basically the situation. Actually, we think this the chiral categorical symmetry can determine the chiral anomalous CFT, but in this one to a few fashion. So there's ambiguity, but ambiguity is not too much. It's understandable. It's controllable. So this is still a very useful thing. Okay. But this number theoretic approach, I feel should be very powerful approach. Should be the future. And but there's a very few study in this. At least I'm not familiar with those kind of things. And so to summarize that, so basically I have this the picture that so any gapless theory or CFT or quantum field theory, when they have this decomposition, then we say that it's a way to reveal the symmetry, and via this different composition, we can obtain the maximum categorical symmetry. And then using maximum categorical symmetry, we probably can largely determine the gapless theory. Okay, so maybe that's what they say. This maximum categorical may be the key to understand and calculate low energy property of a gapless liquid states. Yeah, thank you very much.